Let's first learn about the unit step function, otherwise known as the Heaviside function. This function is written as u sub a of t or u of t minus a, and it's equal to 0 when t is greater than or equal to 0 or less than a, and it's equal to 1 when t is greater than or equal to a. Its graph is exactly what you would expect. It's 0 to the left of a, and then it jumps at t is equal to a to 1, and then stays there. It's simple, but incredibly useful. The Laplace transform of this function is equal to e to the minus as all divided by s. Notice what happens here. A shift in time, that delay of a, introduces an exponential factor e to the minus as in the Laplace transform. Keep that in mind because that is the heart of the second shifting theorem. We can also use the unit step function to turn on any function f of t at t is equal to a. The graph of f of t times u of t minus a is 0 before t equals a, and then f of t switches on at that point. To find the Laplace transform of this function, we'll need what's called the second shifting or translation theorem. We'll talk about that after we work through a couple of examples. We're going to work through two examples step by step where we're going to write a function using a unit step function, and then we'll find its Laplace transform. In our first example, f of t is equal to 0 when t is greater than or equal to 0 but less than 3, and then it's equal to 2 when t is greater than or equal to 3. Let's graph this so that we can visualize what it looks like. We'll let this be f and this be t, and then we'll let this point here be 3. Our function is 0 between 0 and 3, and then at 3 it jumps to a value of 2 and remains at that value. We can write this using a unit step function as f of t is equal to 2 times u of t minus 3. This just means that our function is 2 when t is greater than or equal to 3. Now let's find the Laplace transform. The Laplace transform of our function f of t is equal to the Laplace transform of 2 times u of t minus 3. We can bring the 2 out in front, and we just have the Laplace transform of u of t minus 3. The formula for the Laplace transform of u of t minus a is equal to e to the minus as all divided by s. In our problem, a is equal to 3. This gives us an answer of 2, and then we have e to the minus as, a is 3, so we have e to the minus 3s, and all of this gets divided by s. And there's our answer. Let's look at our second example. I wanted to do one like this because it's just the opposite of what we just did. In this example, our function f of t is equal to 2 at the beginning, and then when t is equal to 3, it becomes 0. Let's go ahead and let's graph this. We have f, we have t, we'll put the point 3 right here, and we'll put this point as 2. Our function starts at 0, and then goes all the way to 3, and we'll put an open circle here, and then at 3, it becomes 0. Here, our function is first on, and then it turns off. We can write this as f of t is equal to 2. That's what it starts out with. and then it becomes 0. So what we have to do is we have to subtract off 2 times u of t minus 3. And that way, it's going to go to 0. Let's now find the Laplace transform of this function. This is the Laplace transform of 2, and we'll go ahead and pull out this next 2. So we have minus 2, the Laplace transform of u of t minus 3. The Laplace transform of a constant is that constant times 1 over s, so this gives us 2 over s, and then we have minus 2, and the Laplace transform of our unit step function, when a is equal to 3, is going to be e to the minus 3s divided by s. We can write this as 2, we'll bring that out in front, and then we have a 1 minus e to the minus 3s, and all of this is divided by s. And there's our transform. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.